Alrighty, folks. Hello and welcome back. This is the end of lesson number 3. And then we have a quick lesson number 4 and 5 to wrap up this module. So this is not going to take too long. So this will probably be a shorter video. And then we'll follow by the next two lessons, which will probably be about an hour and change each. So right where they should be. So far what we've looked at is including categorical variables into our models. We do this using dummy variables. So we started off with something easy with only having a single categorical variable that had two levels, so two different options to it. In order for us to include that into a model, we had to include a single dummy variable. When we had three levels or three options for that categorical variable, we needed two dummy variables. And what we saw was the rule of thumb with this is if we have k different levels, we need k minus 1 dummy variables in there. So again, k levels, k minus 1, so one less. How do we do that? Well, when all the dummy variables are set to 0, they're set to off, that is our reference level. So that is the very first level of our categorical variable, however we decide to order it. I showed you one way to order it. That is just kind of my preference, but it doesn't really matter at the end of the day. As long as we understand what that starting or what that reference level is, then everything is just the difference between the reference level and that new level that we are currently on. So when they're all set to 0, that is the reference level. And then when we activate one of them, and again, only one can be activated at a time. So as soon as we activate one, that is the difference, or that beta is the difference between that reference level and where we would be at that new level. So that's that change in intercept. If there is an interaction between the dummy variable and the numerical variable, how we saw that was not only there was a change in intercept, there was a change in intercept and a change in slope. All right, so the last thing that we're going to be talking about is using squared and interaction variables. All right, so let's jump into the slides here. So first we're going to talk about using squared. So sometimes when we model the data, it is not automatically perfectly linear. We have some curve to it. So we can include in our model that curve as well. So we're kind of correcting for that linearity assumption that we are that is part of the original assumptions of the model. Remember, there's 4 assumptions that we need to make for this. This is one of them, that it has to have that linear relationship between the predictors and the response variable. So when we do in fact have something that is not exactly linear but does in fact have a slight curve to it, we could use a square term or a quadratic term in there. So the quadratic regression model, which is very, very similar to our original model. So our original model is y is equal to beta naught plus beta 1x, and then of course we have that error term, so that plus epsilon. But if we want to take into account that curve, we have to add in an additional term there. We're going to add in a beta 2x squared. So we're just taking the original x data and we are just simply squaring that. So this beta naught plus beta 1x plus beta 2x squared, this is, again, it's the mean value of the dependent or the response variable y when the value of the independent variable is in fact x. So again, what we're modeling is we're modeling what is the average output based upon this given x. Well, that is the what we are looking for. Beta naught plus beta, or beta naught, beta 1, beta 2. These, of course, are our population parameters. These are unknown. We will estimate these based upon the values that we go out and collect for our response and for our different values of x. Epsilon, of course, is our error term that describes the effect of y of all the factors other than x and x squared. So what we get from x and x squared, that epsilon is the difference that gets us to y. So again, we get the, based upon this here, we get the average output to get to the true value is, that's what the difference is, that's our error, that's our epsilon. All right, so the shape of the model, so this is going to be a quadratic. So if we remember quadratic, we have kind of that U-shaped look to it. So it can either be a U-shape, so going upwards, or it could be going downwards. And this is all going to be depending on the signs of our betas. So the quadratic equation, again, this is just saying the same thing as y, but it's just the same thing as saying the y, the average, so you can think of it as the y hat or y bar. So the average for y given beta naught plus beta 1x plus beta 2x squared, that relates, again, the average to the value of x is the equation of a parabola. So here, beta naught Again, no change here. This simply represents our y-intercept of the parabola. So where does it cross the y-axis? Beta 1 is the shift. So if beta 1 is 0, then when it's either at its lowest point or if it's at its highest point, again, depending on if the parabola is going up or down, when it's at its highest or its lowest, if beta 1 is equal to 0, well, that's where it's crossing. If it's not equal to 0, then we're shifting that highest or lowest point over along the x-axis. So we shift it left or right, and then beta 2, the sign of this is, well, not just the sign of this, but the sign of it does in fact tell us whether or not it's going upwards or downwards. So if it's positive, it's going upwards. If it's negative, it's going downwards. But not only that, it's the rate in which it increases too. So the larger it is, the faster obviously this is going to increase. The smaller it is, the slower it's going to increase or decrease, again, depending on the sign of this. All right, so let's look at an example here. So an oil company wishes to improve the gasoline mileage obtained by cars that use its regular unleaded gasoline. Now the company chemists suggest that an additive, and we'll call the additive ST3000, be blended with the gasoline. Now in order to study the effects of the additive, mileage tests are carried out in a laboratory using test equipment that simulates driving under prescribed conditions. Now, the amount of ST3000 blended with the gasoline is going to be varied. So how much we add in, this is going to be our independent variable X. And the gasoline mileage for each test run is recorded, so that's going to be our Y value, that's our response. We're trying to model the amount of mileage that we get based upon the amount of additive that we add in, so the ST3000. So I have the data points here. So we have X, which starts off at 0. So we're adding in no additive, going to 1 unit of additive, 2 units of additive, 3, all the way up to 4. And I have the Y values that go with it. So we've run the experiment. We've tried different things. So 3 different test runs for each different level. So level 0, level 1, level 2, level 3, level 4. Now I shouldn't actually call these levels because they're not really levels. This is a numerical data. We can add in however much we want. So we can go in between 0 and 1. That is perfectly fine. So we're not thinking of this as a categorical variable where I need dummy variables in here. This is simply just a numerical variable. So our model to begin with is going to look something along the lines of y is equal to some beta naught plus beta 1 x plus, again, epsilon, and again, we're going to try and predict what our beta naught, our beta naught and beta 1 are going to be based upon this data. All right, so for this exercise, we have 3 things that we want to be able to accomplish. First thing we want to look at is the scatter plot for the graph. So typically, whenever we're dealing with data, and especially when we're trying to check the linearity assumption, we can just graph this and see if I graph x with respect to y, so do a scatter plot, is it in fact linear? And if it is so, then it is a good idea to model it in such a way that we had before. Chances are, based upon this question, it's not going to be that, and we're going to have to add a quadratic term, but we'll get to that point in time. Part B of this is we want to build a regression model for the data points. And it's not telling us which one we want to use. If I want to use the original model or if I want to use a quadratic, again, we'll get to that in just a second. And part C, what is the predictive mileage if the additive is 0.244 units? Okay. So once we have the model, once we've built the y is equal to whatever we're going to get from there, we want to be able to input a value of x. In this case, it's 0.244. So as I said, it's not a categorical variable where it's 0 amount or 1 amount. We can go in between that. In this case, we are going in between that. We're asking for a 0.244. So not a lot of additive, but if we do that, what is the average mileage we can expect from there? All right, so let's jump into R to be able to do this. So I'm going to switch this screen with this screen here. And let's do that by this. There we go. All right, so where did we leave off? Here we go. We left off at line 73, quadratic models. Okay, so the first thing that what I want to do is I want to bring in the data set that we are using. So I've already uploaded this to Brightspace. It's called gasadd.xlsx. So we're going to bring this in using the read_excel function. So just Control Enter. And notice that again, it can't find this function because I restarted R. Of course I did. So I have to go up to the very, very top. Um, Now, I do this. I don't think it's done by default, but one of the things I typically do because I have a lot of things running is whenever I shut down R, I have it wipe everything. And by wipe everything, I mean it's unloading all of the libraries that I have, unloading the global environment. So sometimes you can just kind of restart R and it's back exactly where you left off. But because I'm jumping around from multiple projects, I just find it's easier for myself just to do kind of a clean slate to this. So I've shut down everything. So I need to reload these packages in. Now I've already installed the packages, so I don't need to install them again. I just need to pull them from the library. So I need to bring in ggplot2. So let's load that using the library function and library read XL. And of course, just to make sure I want to set the working directory correctly, I'm going up to sessions up at the very top here, set working directory, and to source file location, which is simply, again, going to set where it's looking to pull the files from. It's going to be in the same folder that I have this R file in. So this is lesson3.r, and I have it in a folder in my computer, and now it knows exactly where it is. Okay, so let's go back down. No, this went too far. Interaction model, quadratic model, here we go, line 73. So let's bring this in, run this line again, so line 74. There we go. So I have 15 observations in 2 variables, and I can quickly take a look at this by just calling the name of the variable, which is quad data. And in my console, it spits out the 15 rows that I have. So the first column represents the amount of additive. So this is, again, my X value. So 0, 1, 2, 3, and 4. And my second column is my response. So this is my Y. Okay. As I said, the first part, or part A of this, we can see from the question above, is we are looking to build a scatter plot from this. So let's use ggplot to be able to do this. The first layer is going to be the data. So data is equal to quad data. Second layer is setting up the aesthetics. So I want to map the X units, the X values to the units. So again, in terms of the data frame, this is what my first column is called. It's called units. My second column is mileage. So I want to map the y-axis to that specific column of my data set. Then from here, I want to add on my geometry. So I'm going to use points because I'm building a scatter plot. So it's geom_point, and I want to set the color equal to blue. Otherwise, by default, it's set to black. And there we go. Last screen over. Bottom right is the graph. As we see, this is definitely not linear. It starts off relatively small here. It increases up to a point. Looks like it's up to 2. Is this the turning point? Who really knows? We've stopped at 2. But we notice, based upon this, this is the highest point in terms of the data that we have, and then it decreases from there. So there does look to be a point where if we add too much additive to it, we actually have not a decreasing effect, because it's still better than if we add nothing to it. We're still doing better in terms of that regards. But is it better than 2 units of additive? Well, no, it definitely doesn't look like it's better than 2 units of additive. So if I had 4, it's not better than 2. If I had 3, it's not better than 2. So it looks like there is a point that is in fact optimal in here. And this is the nice thing about these sort of quadratic models, when I do have a peak or a valley, depending on, again, the sign of beta in this, or sorry, beta 2. In this case, beta 2 would be negative because it's reaching a maximum and not a minimum. So it has a peak and not a valley. So U, or otherwise an upside down U. All right. So yeah, the linearity doesn't seem to match up here, but it definitely looks like a quadratic model should be appropriate. So we just kind of look above here. So part A, we've done a scatter plot on here, build a regression model for the data. So again, we are assuming based upon A that the model is not beta naught plus beta 1 x plus epsilon as we are not linear. So suggested model would be something like y is equal to beta naught plus beta 1 x plus beta 2 x squared, again, plus epsilon. There we go. So what I need to do now is I need to create a column in my data frame, which I'm going to take the x values and just simply square them. So this is going to happen in line 82. Now I'm going into my data frame quad data. I want to add a new column. So one way I can add a new column is, again, using that $, which references a column. I'm going to name a column that's not already in there. So I'm going to call this units 2 for units squared. Now I have units in there, but I don't have a units 2. So by doing this, this is going to create a new column in my data frame. And what am I associating that with, or what am I assigning to that? I'm taking quad data. So again, I'm calling that data frame. I'm referencing that column for x's, the units, and I'm squaring them by using that, again, that caret 2. So it's taking every element inside of there, it's going to square it, and then it's going to put that vector inside of the data frame, so it's going to add a third column onto there. Okay. So running that. Now notice up in the global environments, quad data is 15 observations in 3 variables, not 2 variables anymore. So first things first, let's build the linear model from this, and then we'll build the quadratic model, and we'll see the difference in these. All right, so to build the quad model, again, using the LM function, so linear model, I'm going mileage is explained by units, not units 2, just units. Again, we're assuming that, well, we'll pretend like we didn't really know that it was quadratic. We assumed it was, in fact, linear. The data is coming from quad data, so if I build this now and run the summary of this, down in the console here, so I have my estimate for beta naught. I have my estimate for my intercept, that's 27.7533. And I have my estimate for my beta 1, which is my units, which is my 0.9. So my intercept, there we go, 27.7533, my slope 0.9. Now, if I were to run a hypothesis test on this, whether or not these are if the true population parameter was equal to 0 or non-zero. Looking at just the p-values alone, my p-value for my units is 0.0196. So that is significant. So based upon this, it looks like definitely that should be added into the model. So it is helping the model. The population parameter is not, in fact, 0. But is the model any good? We'll look at this in more in lesson 5. Lesson 4 and 5 in it itself. But yeah, let's look at this here for a second. I'm just going to point a couple things out because I said we'll talk about this more in detail in the next couple lessons. But one of the things that we looked at back in our first stats class, or stats 2601, was just looking at the r squared. So if I have the r squared value, this is 0.3527. Well, that's not very high. And remember, what is this explaining? This is explaining how the model, or how the model that we've created, oh geez, what's the best way of putting this? Explains the variation in the response variable. So if we're thinking about this in terms of a percentage-wise, only 35.27% of the variation in the response is explained by this model. That's kind of crap. We need to do better than that. One of the things, though, is we shouldn't really look at the r squared if we're looking at multiple values inside of it, or sorry, not multiple values, but multiple independent variables. So right now we're just dealing with one independent variable, not the end of the world. We can look at the r squared, but we'll look at the adjusted r squared in the next little bit when we're adding in multiple independent variables in there. But even looking at the adjusted r squared, and again, I'll talk about more what that represents here, that's a 30.29%. So again, the amount of variation that's explained by this model, still crap. Okay. But we knew that based upon the scatter plot that we have, because it's not linear. It's increasing up to 2 units, but then it starts to decrease from there. So we want to be able to model that curve. So let's build a quad model here. So this is happening in line 88. So we're using the LM function again, and I'm saying mileage is explained not just by units this time, but by units squared. So if I run this, run the summary, notice my intercept has changed. My intercept is 25.71524. So that's my estimate for beta naught. My estimate for beta 1, 4.97619. So remember, this is the shift left or right. So we're being shifted to the right. So the highest peak of this is not crossing the y-intercept. So that's not happening when my x is equal to 0. We've shifted over a bit. As we can kind of see, the peak is happening at at 2 units, not at 0 units. And last but not least, the estimate for beta 2, negative, perfect, because that's what we were expecting it to be based upon the fact that it didn't peak and not a valley, is negative 1.01905. If I look at all the p-values, all of these are significant. So if I were to run a hypothesis testing whether or not the true population for beta 1 is equal to 0 or beta 2 is equal to 0, we would reject the null hypothesis. So again, the null hypothesis is they are 0. They're not adding anything to the model. The alternative is they're non-zero. So it could be positive, could be negative. They're non-zero, so it is adding something to the model. So these are all significant. We would reject the null hypothesis and accept the alternative. Now, I'm not asking for the confidence interval for where the true value is going to lie, because that's not what the question asked. We could do that, but just looking at here, all the values or all the estimates are in fact significant to that. And now also, if we look at the r-squared value, so the multiple r-squared, this is 0.9857. So 98.57% of the variation that we see in the response variable is in fact modeled by what we have here. That's massive in terms of an improvement for when we went from 30% all the way up to 98%. And the adjusted r-squared is also 98.34%. So a major increase. So not only the fact that we were looking at the original model and the parameters were significant, well, they were significant, but the model in itself did not explain the variation, or not well explain the variation in the response. Now we have something that is explaining the variation in the response so much better. All right, so that's part B to this. Build a regression model. So let's write this in here. So part B, the regression model is Y, and I can do this as Y bar, Y hat, whatever we want to keep this as, is 25 point, we'll do 72, 2 decimal places, plus 4.98x minus, rounding to 2 decimal places, is going to get me a 1.02 x squared. There we go. So that's our model. So if I wanted to estimate anything in terms of our model, so for part C, we're simply just saying x is equal to 0.244. I'm going to plug this into here and into here, and I'm going to spit out a y value. Now you can do this with a calculator, perfectly fine, but we have R already set up, so let's do this inside of R. Where is my mouse? Here we go. So what we need to do in order to use the prediction function is I need a model. So we've already created the model. The model is called quad model, and I need a data frame. So the data frame is going to contain the x values that I want to include into my model. So what I need to do for each one of these is I need to build a data frame where each row represents an input, and then once I put it through the prediction function, it's going to give me an output. It's going to get me the predicted y value from there. So the first thing that I want to do is I'm going to build a data frame. It's going to have 2 columns. The first column is going to be called units and units 2. So again, it's going to match the variable names for our model. And notice that my input for this is going to be 0.244, and units 2 is going to be 0.244 squared. So I've created a new data frame. This data frame has 2 columns, has 1 row. That's it. 2 columns, 1 row. So the first column represents units, second column units squared, and that 1 row is going to be 0.244 and 0.244 squared. And if I look at that, that is my output for that data frame. Now, if I go down to line 98, I'm going to use that predict function. So I'm going to call the quad model as my first input. My second input is going to be that data frame. So if I run line 98, what it's going to spit out here is what is my estimated y value. So based upon this, based upon 0.244 for my x value, y hat is equal to 26.86876. And if I look at my graph here, so this is going to be in between 0 and 1, less than 0.5, so somewhere around here. So if this was increasing in the same sort of rate, we would be somewhere along the lines of here. So it would be above 27.5, or sorry, if it's increasing from here, it would be less than 27.5, so somewhere around here. So 26.86, yeah, that looks about right. Again, if we fit that curve and it's hitting the data points as well as possible. Now let's say I wanted to evaluate two things. So let's say I made a mistake. It wasn't 0.244. I wanted 2.44. So what I'm going to do is I'm going to build a data frame with now two columns. Again, same two columns, but I want it to have two rows. So my first row is still going to be the 0.244 squared. My second row is going to be 2.44 and 2.44 squared. So what I'm doing is I'm using the data.frame function, and each input I'm putting a vector in, and that vector represents the column. So if my first column is units, it's a vector, so I'm using that C function that combined, and I'm combining these two elements here, so 0.244 and 2.44. So that's going to represent the first vector or the first column of my new data frame. And units 2 is going to be the second column, and that's going to be the squares of the original there. So if running line 94, then 95 to print it out there, notice again I have that data frame, which I have two columns, two rows. If I use the predict, it spits out two values. The first value, 26.86876, exactly the same. It's not going to change. The Y predicted value is not going to change. It's going to be exactly the same if I put the same values in. But now I have 2.44 as well, so I have 30.79 miles that it's going to get when I add in the 2.4 units of additive. Now let's build a data frame, but this time I want to build a data frame with three columns, one row. So again, using the data.frames function, the first column is going to be units, so that's my 0.244. The second column, I'm calling that units 2, which is 0.244 squared, and units 3. Now I don't have a units 3 in my model. So what's going to happen when I include this? And I'm going to say units 3, this is going to be 1,000. So if I print out the data frame, notice it has, again, that three columns, one row. If I use that predict function on this, 26.86876. Doesn't change. It's not even taking that last column into account. So it's going through the rows, and it's picking the ones that it does, in fact, need. And if I were to change this, let's call this units 3, and this units 2. Oops. Units 2, there we go. Whoop. What in the world is this doing? Stop doing this for a second. We still recording? Hello? Good. Hopefully that didn't freeze. If so, sorry about that. I don't know what I pushed. But we're back now. So we'll go 0.244 squared. And this will be units 3, and we'll call this 1,000. So running this, whoops. No, that's not what I wanted. There we go. Printing that out. So now I've just switched the order. I flipped column 3 and column 2. Using the predict, again, I get the same input. So it doesn't really matter what the order is. It's going to find what it needs to find. There we go. All right, so that's adding a square term. Easy as that. So if we notice something that it does have that peak, or it does have a valley when we're looking at the y with respect to x, so building that scatter plot, well, we just add in a squared term in there. So we can bring this up. Sometimes we need to add a cubic term, sometimes degree 4, not usually past that point. There's usually a point of no return when we are doing these kind of transformations. We can also go down in powers as well. So you might have seen this in the first stats course. If you haven't seen this, this is actually talked about in our, I guess, third year regression courses. So we have courses such as Stat 3503 or 3553, depending if you are a general student. If you're doing the stats minor, you'd be looking at this stuff more in 3503. From an honor standpoint, that's the 3553. So a little bit more theoretical, but again, you'll be seeing exactly the same thing. Just with the 3553, there's going to be a lot more proofs. 3503, not so much. Well, depends on who's teaching it. Still going to be proofs, but it's not going to be as heavy. It's a third year math course or stats course. You're going to have to see some proofs in there. But again, it's not required for your folks' program, but if you are interested in adding on a stats minor, which I always recommend doing, there you go. All right, so let's switch this back up. Where is my mouse again? There we go. Slides. Perfect. All right, so the last thing that we want to talk about is that interaction model, and that's going to conclude everything for lesson number 3. So we've talked about interaction. Well, what does that look like when we are dealing with an interaction between a numerical and a categorical? Again, what we would see if there is in fact an interaction is not only there's going to be a change in the intercept from the different levels the categorical variable can take, but the slope will also be different as well. So when there is no interaction, we just have a different intercept. When we have an interaction, we have a different intercept and we have a different slope as well. Okay, so now what we're talking about is, well, what happens when we are dealing with a numerical and a numerical interaction? How do we manage this? All right. So in a multiple regression model, interaction is said to occur between two predictor variables when the relationship between the response variable y and one of the predictor variables changes based upon the value of the other predictor variable. So what exactly does that mean? So if I fix, say I have two predictor variables, I have 1 and 2. I fix 1 at a specific level and I vary 2. Then we can see, well, what happens to the response? So the response, if I increase x, I might increase y. If I decrease x, I might decrease y. But let's say I increase now, or I change that first predictor variable. So I had it fixed on some level. I'm going to change that level, or change the value that I'm putting in there. So let's say it was 1. Now I'm going to put in a 4. So now it's fixed at 4. And again, I vary that second predictor variable in the same way. So let's say this time around I increase x, but this time y decreases. Or I decrease x and I increase y. Okay, so the response is changing. I'm still varying that second predictor variable, but it's dependent on where I am with that first predictor variable. So there is, in fact, an interaction between those two things. And that's what we're going to be able to kind of test for now. So kind of examples of this, the effect that increasing advertising expenditure has on sales of a product will depend on the unit price of a product. Okay, so if we are trying to model demand of a product, and we look at advertising expenditure and the price of the product, those two things, are there going to be some relationship between the two? Well, we're going to look at an example of that. And yeah, that kind of makes sense. If I vary one, it's going to affect the other. So if I increase advertising or decrease advertising, but I also look at the difference in the price. So I increase the price, I decrease the price. These two things are going to work together. Think of it as you're going into the grocery store and you're looking for a bag of chips. They have the kind of the no-name sort of brand, which is extremely cheap, and you're going to have, say, the Ruffles, but you're ridiculously expensive right now for a bag of chips. One does next to no advertising, one does a lot of advertising, but one is incredibly cheap. Does it need to do a lot of advertising to increase the demand of it? Well, the price is already really good in comparison to everything else around, so it probably doesn't need to spend a large amount of money. It might need to do the bare minimum. Put a sign up or something along those lines. Maybe you don't need to do TV advertising or something along those lines. Or if you do, you're probably not going to see a huge increase in sales because the price is already really good. Versus something that is really expensive, well, you're probably going to have to advertise that a lot to really entice people that this is a great product, that you really want to be spending $100 on a bag of chips. Well, it's not that much, but it's you get the point of it. It's expensive these days. Well, everything's expensive these days. That's the first example. So the second example here, the amount of muscle you gain as a result of weight training will depend on your protein intake. So in order to build muscle, you need protein to be able to do so. But again, same idea. There's kind of this point of no return. If you work out too much, too little protein, too much protein, not enough working out. Again, there's that nice little balance in there. So one is definitely going to affect the other. We're going to stick with the first example here. We're going to run through this one because, well, I already have the data for this. So that's what we're going to be using for this example. So when we have an interaction, so I have two numerical variables, we'll call them x1 and x2. If there was no interaction, so they were independent of themselves, so the effects, there was just main effects, or primary effects. There wasn't a secondary effect from the interaction of the two. They just affected the response independently. And if they did that, then we would have something along the lines of this model here, which is saying we have a beta naught, an intercept. We have a primary effect of x1. We have a primary effect of x2, but there's nothing in between these two things. Now, if there is an interaction between them, we do have that same sort of model here, but now we have an additional term. So I have the primary effect for x1, I have the primary effect of x2, but now I have the secondary effect of the interaction between the two. So that's the x1 and x2. So that's it. I'm just adding an x1 times x2 term. And that beta 3 is going to be, again, we'll estimate it based upon the data that we have there, but that's going to show if I vary, or how things are going to change when I vary my x1 and my x2. Okay. So let's look at the example that we're going to be playing around with. So this is exercise number 5. There's 3 parts to this, but this might take us a little bit of time. We're only at 35 minutes into this, so actually we probably hit the hour, so that's not bad. Just over an hour, full lesson here. So using the Fresh 3 XLSX, so again, this is posted to Brightspace as well for you. So we're using that data. So Enterprise Industries, that's the name of the company, I know, great name, produces Fresh, a brand of liquid laundry detergent. Now, in order to manage its inventory more effectively and make revenue projections, the company would like to better predict the demand for Fresh. So I have, by default, 3 variables here, 3 independent variables, and I have the response, which is the demand. So that's our Y. So X1 represents their price. So that's the price of Fresh. X2 represents the average price or average price of competitors' similar product. So if we're thinking of chips, this could be like the average of the no name. The X1 would be the Ruffles price, and X3 would be, well, how much advertising is spent. Now this is not the advertising for the no name. This would be the advertising for the Fresh, in this case, the laundry detergent. Okay, so what we want to do is we want to build a prediction model. So just using the data that we have, let's build this. Let's see if the estimates are in fact significant, and we'll look at the R squared, or in this case, because we have multiple independent variables, we'll look at the adjusted R squared. Again, I said I'll talk about this in the next lesson, but we'll look at that adjusted R squared, and we'll see how good is the current model at explaining the variation in terms of the response. And can we do better? And that kind of leads us to part B of this. Is there a possible interaction that can be added? Variables combined. So at first, again, part A, we're just looking at the primary effect of X1, X2, and X3. Part B, can we build a better model? Do we know something about this that's going to allow us to build a better model? And lastly, part C of this is we want to describe the interaction. So obviously this kind of answers part B. Is there a possible interaction? Well, if I'm asking part C, describe that interaction, well, yes, it definitely does. And that's kind of a hint for when it comes down to the midterm and the final exam. If you are asked a part C, or additional part on all of this is, how does this change if we do this? And you say, well, it doesn't change. Well, go back. Something was missed at that point in time, because that's the hint. If I'm asking you to describe the interaction and I'm asking in part B, is there a possible interaction? Well, there's definitely a possible interaction. If you haven't got it, then you probably missed something. All right, let's go off to R. I have no more slides. This is my last slide here. Where is my mouse? There we go. So I'm going to bring in my data set. So this is going to be called Fresh Int. So using the read Excel, or read underscore Excel, I'm bringing in fresh3.xlsx. I've already set my working directory. It's all in the same spot, so this should just bring it in normally. Now, this is going to have 30 observations. I don't want all 30 observations. Let's say I just wanted to take a quick peek as to what's going on here. So I can use the head function and input my data frame. So that's the Fresh Int. And it's going to spit out the first 6 rows of that data frame. I can also use the tail function, which is going to spit out the last 6 rows. Now I can change the parameter. I can use n is equal to, and I can say how many rows I want, but by default, it's going to give me the first 6 or the last 6, again, using the tail function. So I noticed this, and this could represent different stores or different regions. So the first store of the first region, the price for Fresh is $3.85. X2 is the average competitor's price, so $3.80. So ours, if we're thinking about ours being Fresh, is 5 cents more expensive. X3, 5.5 units. I don't really know what the units here represent, but again, this is for advertising expenditure, so this could be 5.5 hundreds of dollars, thousands of dollars, millions of dollars, who really knows. And the demand 7.38. This could be, again, it doesn't specifically state how many units or what multiple of units this is, so this could be 7.38 hundreds or 7.38 thousands, so on and so forth. Second region or second store, $3.75. Average price for competitors $4, so in this case we're 25 cents less expensive. 6.75 units in terms of advertising expenditure, and the demand has increased to 8.51. Now the question is the demand, so we see an increase from the store 1 to store 2, we see the increase of demand. Now is that because X3 increased, or is that because if we look at the difference between X2 and X1, there is a greater difference in terms of the price? So we are 25 cents cheaper than the competitor's brand. Is that what's causing the increase in the demand, or is it the fact that we are dealing with advertising? So this is something that we're going to need to look at. This is kind of when we're talking about what interaction is happening here. Maybe there's not an interaction that's happening. Maybe we'll get to that point. But before we get to that point, let's build up the model. So I'm going to build my model. We're going to call this Model 2, which is just going to say why that response is explained by X1, X2, and X3. So again, we're only looking at the primary primary effects of each one. So I'm not doing an X1 times X2 or anything along those lines. All right, so let's run this, run the summary of this. So I'm not going to go through, again, all of the estimates, but this is our estimates. This is our beta naught, this is our beta 1, beta 2, beta 3. If I were to run a hypothesis test for my beta 1, beta 2, beta 3, saying for the null hypothesis, is the population parameter equal to 0? So this would be kind of like, we can see this up top here, my H naught is beta I is equal to 0, where I is equal to 1, 2, or 3, versus the alternative, HA, which is my beta I not equal to 0. So is the true population parameter for each one of these independent variables 0, so it's not adding anything to the model, or is it non-zero? Is it adding something to the model? So in this case, looking at the p-value, these p-values are all significant if I use an alpha of 0.05. So therefore, I would reject in all cases the null hypothesis and accept the alternative. But as we saw before, just doing that, including them into the model, is not necessarily giving us a good model. So that was when we were looking at the linear versus the quadratic. So if I look at my adjusted R-squared, I have 88.13%. So the amount of variation in the response, 88.13% of that variation is explained by this model. It's not bad. Not bad at all. Can we do better? That is the next question. So we've built the model here, so that's part A. Part B of this is there a possible interaction, and can we combine variables? So let's first look at, well, what can we in fact combine? If we look at X1 and X2, do we really need our price and their price? Or do we really just need the difference in price? Let's go with that. Let's take those two variables and we'll shrink them to 1 and just look at what is the difference in price. So I'm going to create a new column. I'm going to call this column X4, and X4 is going to be the difference between their price and our price. So if X4 is positive, this means theirs is more expensive, and if it's negative, that means ours is more expensive. So if I build this, rerun the data frame, notice now that X4, this new column, that first entry in there is negative 0.05. Well, we already knew that because the price for ours was $3.85. Theirs was $3.80. So ours was 5 cents more expensive. And that's what we're getting right here. It's more expensive, so it's in the negative. So whenever ours is more expensive, we get negative. When theirs is more expensive, again, positive. Oops. So in terms of combining, there's nothing really else that we can combine. We can combine our price and their price, but what else do we have? We have advertising expenditure. Well, what does really saying the difference between our price and advertising expenditure help us with? It doesn't really help us with anything. So it's probably a good idea to keep these two things separate. So we've shrunk from 3 variables down to 2 variables. Now, using those 2 variables, does linearity still hold? We haven't actually checked that yet. So let's build scatter plots. Let's look at whether or not this new column X3 and our new column X4 and X3, the original one that was advertising expenditure, if we build scatter plots with these with respect to Y, do we have something that is in fact linear? And I'm going to try and do a line of best fit for each one of these. So the first one, we're going to look at X4. So this is going to be, again, the difference between their price and our price. So if I run this one here, it takes a second. But what I have, again, kind of using this line of best fit, it definitely looks like a line, a linear. It does look like linearity holds. It doesn't look like there is a curve in here. So notice I didn't use method LM, which does a linear model or a linear function inside of here. I wanted to just fit the line as best as possible. So it might not be a line, it might be a curve in here. So fit a curve as best as possible. So in this case, it does look like we have that linearity effect. Now, what about X3, advertising expenditure? Same idea. Well, it does seem like we kind of have a little bit of a linearity, but we also kind of have this little bit of a dip here. So maybe a quadratic term is appropriate. So this would be our U shape. So we would have a beta 2, or the sign for the whether or not we have the valley or the peak. This would be positive. We would have the valley this time. So what does this mean for us? Well, it means for X4, what we just checked the first time around, this is our new variable, the difference in price, we probably don't need to add a quadratic term. But for this one, we may want to add a quadratic term. So we may want to add an X3 squared. So again, I'm looking at what can we add to the model here without even talking about the interaction just yet. So let's build that quadratic term. So I'm going to call this X3 squared. I'm going to include this into our data frame, printing out that data frame. So we have X4, which we've created, and X32, which we've created now. So let's build a model just looking at the primary effects of each one of these. So we're going to say Y is explained by X4, so the difference in prices, X3, the advertising expenditure, and X3 squared. Again, not paying attention to the estimates, just whether or not they are significant. Well, based upon this, X3 doesn't really seem to be overly significant anymore. So maybe we want to remove X3 and just keep X3 squared. But again, if that's alpha of 0.05, we're just slightly above the 0.05. So again, it would fail if we run the hypothesis test, but maybe our alpha is too much in this case. Maybe we don't need to be 95% confident. Maybe only 90% confident is what we would need. And in this case, that would be perfectly fine to include into our model. But again, if we're keeping an alpha of 0.05 and we are being incredibly strict with this, no, that X3 doesn't fit. So we may want to remove that, but keep X3 squared. But let's look at the adjusted R squared. The adjusted R squared is 98. So what were we beforehand? Beforehand, we were 0.8813. So we've gone up, not a huge amount, but we have gone up in terms of the amount of variation that's explained by the model. So it does look like the model is in fact improving. Okay, so let's say I wanted to remove that X3 term because it didn't look overly that significant here. Does that change our model? Well, X4, X32, these are definitely significant. So in terms of a hypothesis test, we would reject the null hypothesis each time. And accept the alternative that these both are adding something to the model. 8828 is the adjusted R squared. So the adjusted R squared actually has gone down. Okay. So even though it wasn't overly significant, having that in there still added something to the model in itself. So in terms of so this is kind of what we'll talk about again when we build the next kind of models around. In terms of predictability, in terms of being able to explain the variation, including it in there seems to be doing a better overall job. But what we really want to do is not only have a predictive power, we want to be able to have an explanatory model. So basically, I want to be able to say, if I increase this parameter here, how does this change my whole system in itself? So if I increase advertising expenditure, well, how do things change? And in order for me to do that to some statistical significance, I need that hypothesis test for each one of those parameters in there. And in this case, that X3, when running the hypothesis test at alpha 0.05, so whether or not the true population parameter is 0 or non-zero, it didn't pass, or it wouldn't have passed. But that doesn't mean it's not adding something to the model in terms of predictability, but maybe explanatory-wise, it's not doing as great of a job. But maybe that's the trade-off that we need. Maybe the predictive power is really more important to us than being able to explain what's happening. All right, so last but not least, let's add in the interaction. So let's include X3 back in there because in terms of predictability, that was good. And now we're going to add in the X3 times X4. And let's build the model here. All right, so notice we have an X4. We have our estimate for that. Our X3, we have an estimate for that. X32, an estimate for that. And now the interaction, X3 and X4. we have an estimate for that. And if I look at the adjusted R squared, 90.83%. So we have in fact gone up. So the amount of variation, more variation in the response is explained by this model. And now actually if you look at each one of the p-values for these, all of these are significant. So x3 is now back to being significant when we add in that interaction term as well. So it wasn't just a good idea to remove it. Let's include everything in there. And then maybe once we have everything in there, then maybe we want to pick and choose what we want to take away. And again, we're going to be looking at this when we're dealing with lesson 4 in terms of the model building. All right, so now what we want to do, so we've built the model. We built our interaction model. And that model looks like what we have here. So I'll write the model down. So this is y is equal to 29 point, we'll do it to 2 decimal places, 1, 1, plus 11.13 x4 minus 7.61. This is x3, so advertising expenditure, plus 0.67 x3 squared minus 1.48 x3 x4. So that's our model. So in order for me to evaluate this model or to plug something into this model, I need an x3 and I need an x4. So I'd have an x3, I would plug that in here, I would square it, plug it in here, and plug it in here. Then I'd have an x4, I'd plug it here, and I'd plug it in here. Okay, so let's predict a couple of things based upon this and see if I can detect the interaction, or if we can see how the interaction kind of works with this. So remember, what I want to do is I want to kind of fix one and vary the other. So what I'm going to do, for x3 and x4, remember when we did the scatter plot for them? So when we did the scatter plot for that, it looked linear. So in order to graph a line, I need 2 points. So let's grab 2 points. Now, if I output the data frame, which I have, where's my mouse? Let's output the data frame here. I'm going to actually do the summary of the data frame. So what this is going to do is it's going to look at each column and it's going to give me a whole whack of different statistics here. So 5 different statistics. So it's going to give me the mean value, the minimum value, the mean, median, maximum, first and third quartile. If I look at, and again, this is going to be for x4, for x4, if I look at the first quartile or kind of like in between the first quartile and the median and in between the median and the third quartile, I have values of 0.1 and 0.3. I'm going to grab some nice numbers into there. So I'm going to do 0.1s and I'm going to do 0.3s. So I want to test x4 at 0.1 and 0.3. So 2 points gives me a line. Now, when we did x3, advertising expenditure, well, that had that kind of parabola sort of effect, that valley sort of effect. So I need 3 points to be able to do that. So if I look at x3, if I look at the first quartile, the mean, and the third quartile, I have values close to, so we'll do x3, of 6.0, 6.4, and 6.8. So what I want to do first is I want to fix x4 at 0.1. So 0.1 is going to see a change in x3. It's going to go from 6.0 to 6.4 to 6.8. So we're going to see, well, what happens to the response at that point in time? And then I'm going to change up my x4 value. I'm going to go, instead of 0.1, I'm going to go to 0.3. And again, using those same x3 values, the 6.0, the 6.4, and the 6.8, I want to see, okay, how does the y value change? How does the response change? And does it respond differently when I'm on 0.1 or 0.3 when I'm dealing with x4? So what I'm going to do is I'm going to build a data frame that's going to have 6 rows So my first column, I'm going to call this X4. X4 is going to be, my first three rows are going to be 0.1s. My last three rows are going to be my 0.3s. So I'm fixing for the first three rows that 0.1, and then I'm going to fix the 0.3s for the last three rows. My second column is my X3s. This is going to see the 6.0, 6.4, and 6.8. So that's going to be matched with 0.1 for X4. And again, 6.0, 6.4, 6.8, that's going to be matched with the 0.3 of X4. So I build this data frame. And I call this pred.df. And again, if I print that to the table here, notice I just have X3 and X4. But I need more than that because my model has an X3 squared and an X3 X4. So I'm going to build a new column, X32, which is just going to take the X3 squared. And I'm going to build a column, X4 X3, which is just taking the X4 times X3. And there we go. I have a new data frame, 6 rows, that has my X4, X3, X32, X4, X3. Now, if I use that predict function, I want to round this to 2 decimal places. I want to round the Y output to 2 decimal places, but I'm using that predict function. So I'm putting in that fresh model. That's the model that I have right above here. I'm using the pred.df, that data frame that was just created, and then again, I'm rounding my output to 2 decimal places. And if I print this out, and I've stored this in a new column in that same data frame called pred. So this last column here is my predicted value. So when X4 is 0.1, X3 is 6.0, I have 7.86. Then I jump up from X3 to 6.4, I get 8.08, 6.8, I get 8.53. And then I change from 0.3 on my X4. So again, this is the difference in prices. So when these again are positive, remember that the competitor's price is more expensive. So for the first one, the competitor's price is 10 cents more expensive. Now it's 30 cents more expensive. And again, we increase the advertising expenditure, 6.0, 6.4, 6.8. And what do we get? We have an 8.31, 8.42, 8.78. So we do see when we spend more in advertising, there is an increase, same as there is here. But the question is, well, what is the rate of increase? So they're both increasing. Are they increasing at the exact same rate? If they're increasing at the exact same rate, that tells me that there is no interaction between these two. That means regardless of what price we put the difference between ours and the competitors, if we spend more in advertising, we're going to see more in demand regardless of how we do it. But if we see a sharper increase when we jump from 0.1 to 0.3, so the difference in price, if we see a sharper increase in terms of the demand, well, then there is an interaction between the two. There is something happening. It's not just the primary effects for each. All right, so let's build this now. So I'm going to build a scatter plot. Well, not the scatter plot. I'm going to do a line graph here. Using the pred.df data as my data frame. So that's my base layer, my layer 1. My layer 2 is my aesthetics. So I'm going to map X to X4. Y is going to be the predicted value. I'm going to group things by X3 and color them by X3. And I want a line graph of this. So if I print this out, so my 3 lines here, my blue line, my green line, and my red line, these represents what happens when I change my amount spent on advertising. So blue represents the most amount spent on advertising. Red means the least amount spent, and in between that 6.4, that is my green. Now notice if I go from 0.1 to 0.3, so I increase, all of these increase as well. And they're not overlapping one another. So that's kind of a key thing there. So that means, well, means a couple of things, but we'll talk about that in just a second here. Well, that means for when it's 0.1, so the difference between the competitors and ours is cheaper by 10 cents. If we increase advertising expenditure, we see an increase in demand. And same idea if we're at 0.3, so 30 cents less expensive than the competitors. If we increase the advertising expenditure, we see an increase in demand. Now the question is the rate of increase the same? So these are all stacked in exactly the same way, where if we spend a little bit more, we're going to get more in terms of demand. But here's the thing. If I go from 0.1 to 0.3, so if ours is really close to the same price, and then there's a big difference in price, if we spend the minimal amount of advertising, we see a sharp increase that's happening there. So what is that telling me right now? When I spend the least in terms of advertising, I'm going to see a sharper increase when there's a bigger difference in terms of price. Makes sense. If ours is just that much more expensive, we're probably not going to need that much in terms of advertising to see a massive increase in demand. Now, on the other hand, if we spend 6.4 units on advertising, we're still going to see an increase on demand if ours becomes less expensive compared to the competitors. But notice the slope of that line is not as steep as this line. So we're seeing an increase, but not as drastic of an increase. And same idea for the blue line. If we spend 6.8 units on advertising, we're still going to see an increase, but again, not as dramatic of an increase. So these lines are not parallel, which would lead me to believe that there is an interaction. If these were parallel lines, that would tell me that, first and foremost, it doesn't matter. There's no crossing of any of these. So if there's a crossing of these, then, you know, if X or the red crossed the green, that would mean that if I went up from 10 cents difference to 30 cents difference, if my red was here and my green was here, I would be better spending less on advertising when I'm at that point in time. But I don't see this crossing. But they're not quite parallel. The slopes are different. They're kind of the same, but there is a difference in here. So if the slopes are different as well, so if there's a crossing or the slopes are different, then it is telling us that, you know, if we increase here, the demand or the increase in demand is going to in fact change. Now I could flip this, so I'm going to get the same idea. So this time around, I'm going to put my X as my X3, and I'm going to group things by X4. I'm going to get the same idea in the end, just kind of a different visualization of this. So across my X-axis, this is my advertising expenditure. So if I spend 6, 6.4, 6.8, again, if red here is the difference of 10 cents versus the difference of 30 cents, if I spend 6 units, obviously I'm going to see more of a demand when there's a greater difference in price. If I spend 6.8 units on advertising, again, difference in price, still the key one there. But again, notice the difference between these two. When I'm only spending the minimum amount on advertising, that's 6 units here, or I'm fixing it at 6 units, I have a much larger gap between the two, which is telling me here when I'm spending that little, price is very significant. At 6.8, when I'm spending the most amount on advertising, there still is a difference, but it's not that big of a difference. So is price really the key factor here, or is the advertising really the key factor here? Here, the price is definitely a key factor here. Here, that could be the advertising that's doing it. Okay. So again, they're not parallel lines, which leads me to believe that there is an interaction effect here, which, again, going back up to my model, I look at my X3, X4 term. I have 0.036105. This is my p-value. So if I run the hypothesis test asking, is the interaction term 0, meaning that there is no, in fact, interaction, or the alternative, it's non-zero. Doesn't matter if it's positive or negative. If it's non-zero, I should include this into my model. At alpha of 0.05, I would reject the null hypothesis and say, yes, it is appropriate to add this to the model. There is a statistical significance that there is, in fact, an interaction between these two variables. And we've seen this here. Okay, so that's it in terms of adding squared terms and interaction terms. Well, that actually puts us up to a full lecture. Excellent. I thought this would be a little bit faster. Sorry, but thank you for sticking around as always. And now we'll be jumping into lesson number 4 and lesson number 5. So there's going to be one video of each one of these. I think they might be a little bit longer, but we'll get to them. That's it. That's all for today. If you have any questions, comments, concerns, feel free to reach out. Otherwise, we will see you back the next time around. And where is my mouse? Here it is. Stop recording.